It looks like the people joining the Zoom have slowed down a bit, so maybe we can get going. It's my pleasure today to introduce Duo Chan. Duo is presently the Weston Howland Jr. Postdoctoral Fellow at the Woods Hole Oceanographic Institute. Before joining WHOI, he completed his PhD with Peter Hybers at Harvard University, following a master's in meteorology from Nanjing University. In his work, he developed statistical and physical tools to reconstruct past climate and understand climate variability, with a particular interest in the Earth's thermal variability. He's worked on a number of different exciting problems. I'm sure we'll get a taste of some different things today, but ranging from the role of sea surface temperatures in hurricane genesis to looking at sea temperatures, both ranging from the ocean interior to the surface, and also some questions about temperature variability. On a personal note, Duo and my first significant interaction was at a climate summer school in Norway when we were both PhD students. And we were both assigned this project to work on. And I was like, okay, this is a pretty hard project. Like, we're not going to make any headway during the summer school. And I swear that Duo had like finished the project by the next morning. And now it's been published and there's some more complexity, but anyway, he's a brilliant guy and very efficient as well. It's no surprise to me he's done a lot of great work since that summer school, and I'm excited to hear more about it today. So take it away, Duo.
Well, thank you, Jane, for the introduction, and thanks everyone for coming to my talk. Right, so today I'm going to talk about some of my PhD work. Actually, I've just joined WHOI 3 months ago, so these are still most of my PhD work, of combining statistical, historical, and physical evidence to improve the quality of historical in-situ sea surface temperature records. So this work is in collaboration, of course, with my advisor, Peter Hybers, but also with scientists and researchers from other institutes. And most of the material that I put up today is about 15 minutes. So I think let's just get started. So these in-situ sea surface temperature measurements are crucial for us to study weather and climate. These temperatures are mostly defined at an ocean depth of around 20 to 30 centimeters. They're widely used, for example, to monitor long-term climate change or to define major patterns of climate variability like the Pacific Decadal Oscillation or the Atlantic Multi-Decadal Oscillation. They're also used to understand extreme weathers like hurricanes and droughts. Sometimes these measurements, basically these in-situ measurements at the sea surface, are used to calibrate remotely sensed temperatures from satellite. And of course, if you run atmospheric model, there is one type of simulation where these sea temperature measurements are used as a boundary condition to drive the atmospheric component. So given the importance of the sea surface temperatures, you may think, well, so we must have a good understanding of the quality of these in-situ sea surface temperatures. But actually, the quality of them are questionable even in the most recent 20 years, when we think we must have sufficiently good technology to measure theirs. So this issue is related to a phenomenon called the global warming hiatus, meaning a slowdown of the warming rate. And this red curve is an older version of a global mean temperature estimated by NOAA. As you can see, the warming rate actually slowed down after 1998. But this group of scientists at NOAA has realized, oh, so actually these ship-based measurements need some additional corrections. Also, during this period, since the 1980s, there's an increasing proportion of measurements coming from drifting buoys. And compared with ship-based measurements, these drifting buoys are relatively colder by around 0.1 degrees Celsius. So all these offsets needs to be accounted for. And after making corrections, the black line is their new estimate. As you can see, the warming rate after the 1998 becomes more consistent with warming in the earlier period. So this biases in sea surface temperature really changes our anticipation of what future warming could look like. Problems, of course, also happen in earlier period. And for example, in this 2008 paper, Thompson et al. Reported a large discontinuity in global sea surface temperatures. So in this figure, they showed the global mean temperature estimated from the UK Met Office. And they have also removed variabilities associated with ENSO and other major patterns of climate variations. So in this residual curve, what is most prominent, I guess, is this sudden drop by around 0.3 degrees Celsius at the end of 1945. And quoted from their paper, this abrupt temperature drop is an apparent result of uncorrected instrumental biases in sea surface temperature record. So why having a reliable historical SST measurement or estimate is difficult? Well, to understand that, we probably need to understand how things were measured in the first place. So back in early days, most ocean temperatures were not taken by dedicated climate scientists, but by regular sailors as fishermen, soldiers, or merchants. So not for the purpose of studying climate change, but for helping them to navigate. Nowadays, these measurements seem to have irreplaceable value because they are the only direct measurement of the past ocean state. However, until the 1950s, as you can see, most of them were taken by dropping buckets into the ocean and measuring temperature of water in buckets on ship decks. During the process of measurement, water temperature can become colder by several tenths of a degree Celsius because of wind evaporation. And I think you probably can tell how large the wind is from this guy's messy hair. And in other cases, these buckets could be heated by the sun during the daytime. So if we are to use these biased data out of their historical context and to study climate change that is only within 1 degree Celsius throughout the entire 20th century, we have to account for these instrumental biases. Yet accurately accounting for bias is not easy. Because of limited metadata, previous studies all made simplifying assumptions, such that all bucket measurements in the same year are biased in the same way, as if they were measured by the same person using the same bucket. So to be more specific of what I mean, these corrections often use a fixed large-scale pattern to represent SST biases and a smooth time series to represent changes in the amplitude of that pattern. For example, early versions of Hadley SST, or the estimate from the UK Met Office, used a thermal bucket model to simulate pattern that looks like this. And they assumed a linear increase in the amplitude.
Duo, you've muted yourself.
Sorry, when did you lose me?
Oh, just a couple seconds.
Okay, thanks. So they actually assumed a linear increase in the amplitude of that pattern, which may or may not be reliable. Although different data sets may have used different patterns or used different ways to estimate these amplitudes, most of them all made the simplifying assumptions by treating all bucket measurements as coming from the same source. However, bucket bias depends on types of buckets being used and measurement protocols being followed. For example, a canvas bucket can be additionally colder by around 0.5 degrees Celsius compared with a more insulated wooden bucket, even measured under the same condition. Besides buckets, sea surface temperatures were also collected using other methods that have distinct biases, which I'll cover in later part of this talk. Problems may also happen after data collection, as information transferred from the original logbook to punch card, tapes, floppy disks, and all the way to the modern data set. As a result, anything in this complicated network could go wrong. So in addition to correcting for biases common to all SST measurements, we may also need to account for unique biases associated with individual groups that may have arisen from distinct physical or historical reasons. And this is what I've been doing during the past maybe 5 or 6 years. And because metadata detailing the measurement practices is often too limited to physically model specific biases, and because these physical biases could be compounded with data management problems, I in turn take this problem from a big data or a data science perspective and developed a statistical method to first detect and quantify how individual groups differ from one another. And my method works like this. We first group data according to their instrument, so the way or the methodology, for example, buckets or non-buckets, their nationality, and a number called deck number, which represent the purpose of their ships. For example, some ships are merchant ships, some are naval ships. Sometimes this deck number also carried information about who post-processed or digitized the data. So after putting data into groups, we actually assume that measurements in the same group share the same kind of bias, so they're homogeneous. But between groups, things are heterogeneous. So we then compare measurements from different groups when they're ship passing nearby. So at this point, the sailors were actually measuring the same part of the ocean at around the same time, and we will have a chance to tell which group is relatively warmer or colder. And specifically, we use 300 kilometers in space and 2 days in time as the criteria. One thing that worth mentioning is that each measurement is used at most once, basically to avoid correlations of errors across pairs. And our algorithm prioritizes pairs that are closest in space. So this idea is simple, right? But actually the data set is huge. And the amount of data that we need to handle at the same time can easily go beyond 10 million pairs. And in our most recent analysis, we're actually handling more than 60 million pairs at the same time. Things can be even more complicated because, within a pair, these measurements are not always perfectly co-located in space and time. For example, measurements that are closer to the equator or taken during the daytime are expected to be warmer, which we have to account for by using high-resolution climatologies estimated from satellites and also drifting buoys. We then model this residual differences within a pair using a linear mixed effect model. So before digging into the details of the mathematical equations, let me first give you some high-level overview of what this model is doing. So in general, it does two things. First, it estimates systematic differences between individual groups relative to the average of all paired measurements. So in this scheme that has three groups, what the model estimates are indicated by these colored arrows as distance relative to the average of all of them. At the same time, the method also estimates how these group-wise offsets may have varied with region and time, such that we will have more degrees of freedom to represent and explore data heterogeneity within the historical archive. So if we put things in this mathematical equation, this is the model. So first, this residual difference is modeled as differences in mean offsets associated with individual groups. And here, this X is a design matrix whose entries are 1, -1, and 0, indicating which two groups are being compared. And alpha is a vector containing mean offsets associated with individual groups. So in fact, if this model only has this part, the whole analysis will be the same as a multiple linear regression because this alpha term is treated as a fixed effect. However, on top of the mean, right, these offsets may also vary with region and year, which we also account for, but as random effects. So to write out, let's say for the regional effect, here this ZR is a much bigger design matrix, but its entries are also 1, -1, and 0. So what the ZR differs from X is that it needs to indicate not only which two groups are being compared, but also where that comparison is happening. So accordingly, this beta is a longer vector detailing for each group, right, how that offset could have varied in individual regions around the mean offset. So all elements in this beta vector is actually assumed to follow a normal distribution, such that this model will actually relax these solutions towards zero when there are fewer data available for estimating individual offset effect. And this is also why this model is called a linear mixed effect model, by combining these fixed with random effects. And so at the same time, the yearly effects are assigned in a similar manner. And finally, we have these residual terms, which on its own is also has like a complicated error model, and we actually carefully budgeted the error sources. So in general, it has two major sources. The first is physical SST variability. For example, the SST difference between the 2 points, right? Although they have a climatological difference, that difference will vary from year to year. And also for the day-night difference, the diurnal cycle would also vary from day to day, depending on the weather patterns. So this is the first source. And at the same time, we would also need to model random or partially correlated observational errors as well. So we solve this model iteratively between these alpha and the covariance of these beta terms until we reach a maximum likelihood estimate. And my first application of this model is actually to, so by the way, I think maybe some of you may have realized that this model is designed to only account for relative offsets between groups, right? But in fact, it's likely that all groups are biased from the true temperatures. So this is actually what I'm doing now as a postdoc at HUI by developing an absolute bias correction that takes into account air temperatures from coastal and island stations, as well as changes in the diurnal cycle of sea surface temperatures. So this correction would account for this additional distance between this dashed line and the solid black line, which will give us an absolutely corrected sea surface temperatures. And hopefully, maybe within the near future, if I can give another talk, I would talk more about these absolute corrections and new insights that we gain from this additional correction. But right now, maybe let's just focus on these group-wise offsets that is detectable by this existing LME model. So I first applied this model to measurements that are thought to come from buckets. And this intercomparison contains about 18 million pairs of data coming from about 150 groups. So after running the model, this figure shows the fixed plus yearly effect for individual groups. So as you can see, the x-axis goes from 1850 to 2014, and the y-axis are the name of individual groups. And here, because we are only intercomparing bucket measurements, groups are identified only according to nation and that deck number. As we can see, these offsets can range from more than negative 0.5 degrees Celsius to more than positive 0.5 degrees Celsius. And in most groups, these offsets are quite consistent with time, although in some cases, these offsets can change its sign very dramatically. For example, in this Japanese group, the sign of these offsets actually changed in the 1930s, which we will also cover later in my talk. So let's talk about some statistics. As you can see, right, the fixed effect of 49 groups are significant with a p-value smaller than 0.05, as indicated by these single stars. At the same time, we're really performing a multiple hypothesis testing in this analysis. So in order to control for the family-wise error rate, we apply a Bonferroni correction. And after this correction, still like 6 groups remain highly significant, as indicated by these double stars. And we have tested the sensitivity of these results by performing different model formulations, by playing with the parameters and testing the assumptions made in these statistical models. The conclusion that significant offsets between nation depth groups of bucket SSTs is actually robust. So let's put a brief summary here. Now we find significant differences between groups of sea surface temperature measurements. And because different groups are sampling different part of the ocean at different times, these offsets would map onto the heterogeneous distribution of individual groups and lead to regionally and temporally varying biases that were not accounted for by previous correction schemes. But before using these statistically determined results to making adjustments or corrections, I think it's always important to really understand what the statistical or data science or machine learning method is telling us. And we combine physical and historical evidence to understand the statistically determined offsets. So we actually have several papers focusing on this aspect. But today I probably will not have the time to focus too much on this. But instead, I would like to share one story with you. So this figure shows the estimate of differences between bucket measurements for several major collecting nations in the early 20th century. As you can see, there is a sudden drop in the offset of these Japanese measurements in the 1930s. So in fact, this Japanese group contributes to nearly all Japanese measurement at that time, and they dominated the data source in the North Pacific. So understanding why this drop happened becomes important. What has happened? Was it because the Japanese used a new type of buckets or something suddenly changed in the post-processing of the Japanese data? Well, actually, we made many trials and errors. For example, one of our assumptions was that as the time approaches the Second World War, the Japanese really need to have bigger ships such that they can traverse across the open ocean. So when you're measuring a bucket on larger ships that have a higher deck, right? These bucket measurements could be colder because of longer time that is taken to haul the buckets and also relatively larger wind that the bucket is exposed in. But later we actually find historical and physical evidence that disapproved this hypothesis. So for example, we actually developed a physical model to simulate how the temperature of water will cool or change when they were measured on ship decks. And unfortunately, this model only suggests that maybe this change is within like 0.1 degrees Celsius. And at the same time, it is kind of like interesting because I actually went through a database that documented the history of individual Japanese naval ships. And when I was reading through the literature or historical documents, I just realized, well, although these size of Japanese ships become bigger as it approaches the war, but nearly all these large Japanese ships actually sank during 1942 to 43 during the battle with the US navies. And all those new ships made as replacements were actually small in size. So if that hypothesis was the reason, right, you would expect things to go back after 1945. But in fact, this cold anomaly goes all the way to the 1960s. So there are also many other trials and errors until we eventually came across one document, and the result actually is quite striking. So according to this document, it says that the Japanese data were actually digitized by different people. And when the US Air Force were digitizing data after 1930s, basically from the 1930s to the 60s, they truncated the temperature, dropped the decimal, and just floored everything to the whole degrees Celsius. So no wonder the temperatures become colder relative to other nations. And we also tried to use, in addition to these historical documents, we also tried to use diurnal cycles to understand the origin of other offsets, which I'll cover in later part of this talk. So in short, right, with physical and historical evidence supporting these statistical results, we're much more confident that we can better remove these biases and provide a refined sea surface temperature corrections. And indeed, the corrected data set actually brings many new insights for understanding past climate change. So for today, I will give you 3 examples. And the first one is about the early 20th century warming. So I'm not going to spend too much time on this part because the paper was actually published 2 years ago. So you can always refer to that paper. And also, if you are interested, I'm happy to talk more about this after this seminar. So in short, without group-wise adjustments, this figure actually gives the averaged SST evolution in the North Atlantic and the North Pacific during the early 20th century. One prominent feature is that the North Atlantic actually warmed much faster, in fact, more than twice as fast as the warming in the North Pacific. Such a different warming rate was actually hard to understand because none of the climate models were able to reproduce this big discrepancies in the warming rate. So previous studies have suggested that, well, this must be arising from an unusually large expression of internal variability. But now we know that these Japanese measurements after the 1930s are truncated, and the Japanese measurements dominated the North Pacific. So after correction, the new estimates looks like this. As you can see, the warming rates actually becomes much more consistent between basins. So now we know that this so-called discrepancy in the warming rate is nothing physical. And this new estimate, right, actually suggests a dominant role of human activities in driving this early 20th century warming. And the rationale is because the CO2 that we emitted into the atmosphere are more or less evenly distributed. So this more uniform early 20th century warming is my first example. As my second example, I would like to first bring you back to this figure documenting the NOAA temperature estimates. I guess compared with what happened in the last 20 years, a more prominent feature in this plot may be this warm anomaly during the World War II period. As you can see, temperatures in 1945 can be even warmer than some of the years in the 1980s. Interestingly, this warm anomaly is only seen in the sea surface temperature component of this NOAA estimate. So I'm showing this most updated version of the sea surface temperature component, so the NOAA estimates in this figure. As you can see, the warm anomaly is still here. In fact, it's not only in this NOAA estimate, in the most recent Hadley Center or the UK Met Office estimate, we also see a warm anomaly by around 0.2 degrees Celsius. So if this warm anomaly is real, it will have implications for us to understand, for example, the magnitude of early 20th century warming, the mid-century hiatus, the relative contribution from internal variability versus external forcing, and many related stuffs. Several years ago, I actually met a retired high-energy physicist who is senior enough to witness World War II. And he told me that he believed, this warm anomaly must be something physical and real because the US factories were making weapons at their full capacity and emitted a huge tons of carbon dioxide. However, as an ESS department, right, we all know that the climate doesn't work like this. At least the greenhouse gases has a much longer lifetime than 5 years. So even if it could drive this warming, you would never expect things to just go back directly after the war. And in fact, these gray curves are what CMIP5 models can simulate when forced with known historical forcing. And the bottom line is that no climate model can reproduce this observed World War II warm anomaly. Of course, we know that these models are not perfect, and I often hear people criticizing these CMIP projects. But at the same time, right, although models are not perfect, data could also be wrong. And it actually is very likely the case during World War II, a period that actually experienced unusual changes in the way that people use to take marine meteorological measurements. So the first change is the change in the measurement instruments, which has been suggested by this Thompson et al. 2008 paper. Sometimes, you can see the paper was published 12 years ago, but we still see problems in the sea surface temperature data set nowadays, right? So their rationale works like this. So before and after the war, most of the temperatures were taken by the bucket measurements or the bucket method that are coldly biased. However, during the war, there is an increasing proportion of data coming from the US and UK naval ships. And these big naval ships actually use a different method to collect sea temperatures. It's called the engine room intake method. So this method works like this. Because these big engine ships need to pipe in seawater to cool the engine room, they would also need to monitor the inlet and outlet water temperature such that they need to make sure the system is working properly, right? So the temperature of the inlet water is taken as a proxy of SSTs. Well, you may imagine like, oh, well, these big engine ships and the pipe-in depths are typically at about 5 to 15 meters. So it's a much deeper depth. So their sea surface temperature measurements should be relatively coldly biased. But unfortunately, these measurements are warmly biased because of heat released from the ship engine. So associated with this change in measurement method is the change in the sign of biases. And this could lead to a positive wartime anomaly. So to better demonstrate this point, we just separate measurements coming from buckets or engine room intake measurements. And as you can see, either of them, when plotted separately, show a big World War II warm anomaly. It actually is when we combine all available measurement that this warm anomaly appears. So the second type of change involves taking nighttime temperatures inside ships to avoid lighting a torch on the ship deck being detected and destroyed by your enemy. So Folland et al. Has reported a warm anomaly of around 0.8 degrees Celsius in the nighttime marine air temperature measurements during the wartime. Although nothing has been reported for sea surface temperatures, it is likely that these bucket measurements were taken outside, but also taken into the ships and read indoor. And when you're reading these measurements indoor in a warmer room temperature and much smaller wind exposure, the buckets are less coldly biased. Of course, previous studies must have somehow accounted for these problems, right? So to some extent, but obviously they didn't do a good job. So why that's the case? Well, one type of correction as adopted by ERSST or the NOAA estimate, they did not even try to distinguish between the bucket and ERI measurements. What they did is they simply clumped everything together and referenced the sea surface temperature to a third-party temperature, which they chose the nighttime marine air temperatures. However, using this framework, right, the corrected sea surface temperature will rely heavily on the reference temperature that you use. And these nighttime marine air temperatures are not even a good reference to start with. For example, they suffer from the bias of being taken indoor, right? And also people have been realizing that and using daytime counterpart to replace these nighttime measurements during the wartime. But the daytime temperatures on their own have complicated biases due to solar heating. So that may not give you a very clean correction of the sea temperature. In addition, using this method by clumping everything together, it's almost unlikely to attribute data problems to specific subsets of measurements, as what we said about that Japanese truncation problems. So there is another type of data set that used a different method. They tried to basically separate the bucket and the engine room intake measurements. So this is adopted by Hadley SSTs. Compared with this estimate, I think it's better, right? But because of limited metadata, they would also need to assume many things. For example, the relative differences between these bucket and engine room intake measurements, and also in many cases, the measurement method of individual sea surface temperatures. So given these limitations, it's actually very likely that previous estimates may have not fully accounted for data problems. But the LME method, or the linear mixed effect intercomparison framework, actually is very suitable for looking at this problem. First, we do not necessarily need a third-party reference temperature to understand what happened during this 15 years. And also, it estimates the engine room intake and buckets offsets directly from the data. And we do not need to assume the method for unknown measurements, because we can simply group them into one group, but of course separated by nations and other informations, and then let the model to determine what is the required adjustments for these unknown measurements. And finally, right, because of our group-wise assignment, we can actually perform more detailed and refined corrections associated with nation and other groupings, such that we can attribute problems to specific SST or data problems. So right now, what we're going to do is to apply the similar method, but to homogenize not only bucket, but also measurements coming from other methods, like the engine room intake and those without a method information. And in this comparison, we're handling about 50 million pairs from about 500 groups of data. And even during the 15 years around the World War II period, there are still about 2 million pairs. And here I'm showing the averaged offsets during the period around World War II for the 66 groups. As you can see, still we detected significant differences, and things range from being coldly offsetted to being warmly offsetted. So is there a way that we can physically understand these offsets? Well, one way to evaluate the statistical model's result is to look at the amplitude of diurnal cycles, or the day-night differences. So in general, when we plot the group-wise offsets against the diurnal amplitude, we would expect a negative relationship to emerge. And the rationale is that bucket measurements are coldly biased, but they should have a larger diurnal cycle because they also suffer from additional solar heating during the daytime. On the other hand, these engine room intake measurements are warmly biased, but because they are taken at a much deeper depth, they actually has a smaller diurnal cycle. So when we plot the relative offsets against the amplitude of diurnal cycles, we do see this expected negative relationship emerge from the data. And all these positively identified bucket groups are on the colder end, whereas these positively identified ERI groups are on the warmer end. Another thing that I think I need to mention is that here we only have 33 groups as 33 dots. And it is because, for many of other groups, we don't have a data quality that's good enough for us to estimate a reliable diurnal amplitude. So in short, the offsets between these positively identified ERI groups are about 0.5 degrees warmer than these bucket groups. And this offset is actually about 0.1 degrees higher than what is assumed in that Hadley or the UK Met Office estimate. At the same time, we can also use this relationship to estimate the measurement method for SSTs without a method information. So basically, we found that most of the missing information, SSTs without a method information actually come from US measurements, which account for about 95%. And all these US groups, as indicated by these cyan circles, sit on the small amplitude but warmer ends. So indicating that these US measurements were actually 100% ERI origin. Again, this percentage is also higher than the 88% as assumed in the Hadley SST4 estimate. So we are confident that the LME method should more fully remove data heterogeneity. And after correction, the new estimates changes from this to this. As you can see, things are much more homogenized, and the World War II warm anomaly is much more damped. And if we quantify this anomaly as the mean during the wartime minus the mean in the surrounding 10 years, it actually decreases from 0.4 degrees Celsius to only 0.13 degrees Celsius. So as I mentioned, right, one benefit of this method is not only it removes the biases, but it also tells us which group contributes to these data problems. So what is shown in this figure as a stacked bar is the contribution of global correction from individual groups. And you can see during the wartime, the correction mainly come from two groups. One is this US naval ship that contributes to about 0.2 degrees of correction. And the other is this UK Royal Naval ship contribute to another 0.06 degrees of correction. So these ships basically used the ERI measurements during the wartime, and basically our method successfully detect and remove that signal. But there is also another hypothesis, remember, that is, are nighttime temperatures taken inside the ships? So to test this hypothesis, we simply separate daytime and nighttime only bucket sea surface temperatures. As plotted in this figure, you can see that, well, the nighttime bucket measurements also show a warm anomaly by around 0.3 degrees Celsius, which is not seen in the daytime counterpart, nor in these engine room intake measurements. So we believe that this is also a strong indication that these nighttime bucket measurements were taken, or at least read, inside ships. And we ended up performed a final analysis that used only daytime measurements. And the final estimate looks like this. Qualitatively, it's very similar, right, to what you just saw, but quantitatively, removing these biased nighttime measurements further reduce the group-wise adjusted, further reduce the estimates of World War II warm anomaly to be less than 0.1 degrees Celsius, which is not significant at the 95% confidence level. And finally, we compare our estimates in the context with climate models and also with other estimates. So here, this red dot is our final estimate. Again, you can see that it lies within the 95% coverage interval of internal variations as simulated by both CMIP5 and CMIP6 models. This is the NOAA estimate, which is definitely an outlier. This is the Hadley Center most recent estimate. You can see they have a very large error bar because they wanted to acknowledge that there are many unknowns in the data set. But actually these can be detected and quantified using this intercomparison scheme, and this error bar can actually be reduced to a great extent. There's another point, which is this Calton SST, that also give a very much damped World War II warm anomaly. So this data set actually used a similar method as these NOAA estimates, but they used a different reference temperature, which is the air temperature from coastal and island stations. Again, the method adopted by them would require the corrected sea surface temperature to look like these station temperatures. But our estimate actually showed that, these sea temperatures, or the World War II anomaly in sea temperatures, are directly an effect of data problems associated with changes in measurement instruments and measurement practices. But in any cases, once we account for these data problems, the sea temperature and the coastal land temperature are actually in good agreement. So the removal of this World War II warm anomaly is my second example. And as my last example, I would like to show you that in addition to simple sea surface temperature evolutions or these linear trends, these group-wise adjustments also have implications for understanding systems in the climate, and that would have direct social implications. So the example that I used here is hurricane simulation. So quoting from the Knudsen et al. 2020 paper, the modeled tropical cyclone frequency projections are less robust for individual basins, even in terms of the sign of projected changes. So reading from their figure, the 90% confident coverage interval of projections for the North Atlantic hurricane frequency can range from a 35% decrease to 30% increase among different studies. So one prerequisite for accurately predicting these future changes, right, is to reproduce and understand how and why things have changed in the past. And actually, by looking at historical data, people have already built up a link between the North Atlantic hurricane activity and sea surface temperature patterns. So this variability or this linkage is through an index called relative sea surface temperature variability. So in short, the decadal variability of the North Atlantic hurricane frequency would co-vary with the SST difference between the main development region and the rest of the whole tropics. And as you can see on this figure, which shows the 5-year running averaged hurricane frequency reconstruction, and also a relative SST index from 2 existing sea surface temperature estimates. So a brief investigation is that, well, they both show decadal variations that are generally agree in phase. So there is a good relationship. But if we take a closer look at specific period, we would note that things actually do not agree that well. For example, in the late 19th century, the hurricane activities were actually very active, but you barely see a positive anomalies in these relative SST index. Similarly, during the mid-century, the hurricane activities are damped relatively, but the sea temperatures are actually in a positive phase. In fact, similar discrepancies also exist when we use these existing SST dataset to force high-resolution atmospheric models. So shown here is a similar comparison, but between the observed and simulated hurricanes. So let's first talk about this observed hurricanes. It actually consists of 2 parts. The first is the number of hurricane tracks from the HERDAT dataset. And the other thing is a correction of potentially missed hurricanes before 1965, so before the satellite era. And I would like to mention that this curve is 15-year averaged, and we have already removed the beginning and ending 7 years from this plot. So you're not seeing, like a smoothing effect for this high value. And then this dark blue curve shows the simulated hurricanes when forced by Hadley SST1. So here we actually have 8 ensemble members, with 5 coming from GFDR Hiram that have a 50-kilometer resolution, and 3 members coming from another model having a 25-kilometer resolution. And these uncertainties are 95% coverage interval. So basically, for the observations, it has 2 components. One is the intrinsic atmospheric variability, which is the sensitivity or random noise in relative to different choices of initial conditions. And the other is contributions from this uncertain hurricane adjustments. But as you can see, right, because we did not perform any correction after the 1960s, so everything here are actually representing the intrinsic atmospheric variability, which you can see constitute a relatively big portion of the observed error estimates. And this shading curve and this blue shading are estimates for model simulations. It's narrower and it actually only contains intrinsic atmospheric variability. It is narrower because this is an average over 8 ensemble members. Okay, so I guess like the bottom line from this figure is clear that these high resolution models, when prescribed with Hadley SST, showed too few hurricanes in the late 19th century and too many in the middle 20th century. This is not a good news, right? Because the inability to reproduce the past would erode their credibility for future projections. And this low reproducibility can actually arise from many different reasons. For example, that observational reconstruction was wrong, or there are important processes not correctly represented in these models. But at the same time, problems may also happen in the data set that we use to force or drive these model simulations, like SSTs. And in fact, this group-wise bucket adjustment changes the pattern of sea surface temperatures and the relative SST index. So as an example, what I'm showing here is the map of averaged adjustments over 1885 to 1920s. As you can see, these adjustments generally followed the ship tracks, and it actually warmed up the Atlantic and cools the rest of the Pacific, leading to an increase in the relative SST index. One thing that I would like to mention is that although these group-wise adjustments are only on the order of 0.1 or maybe 0.2 degrees Celsius, these adjustments actually are large in the sense that the magnitude of the adjustments are comparable to the range of projected changes under, let's say, the RCP scenarios in the future. So if we look at the temporal changes, this is what it looks like. As you can see, the group-wise bucket correction increases RSST in the late 19th and early 20th century and decreases RSST in the middle 20th century. And things tailored towards zero because we have a declining percentage of bucket measurements. So following the argument or the rationale that relative SST controls the North Atlantic hurricane counts, we would expect the simulated hurricanes to also increase in the late 19th century and decrease in the middle 20th century. As a result, we performed another set of simulation by adding these bucket corrections to the existing Hadley SST1 dataset. And the result looks like this. As you can see, so basically as expected, right, things increases in the late 19th century and decreases in the middle 20th century. And here I'm showing the difference between the red minus the blue curve. So to show you what is the change associated with our SST adjustments. And these green shadings represent the error across 8 models, 8 model ensembles. So in short, the simulated decadal variability of the North Atlantic hurricane actually becomes more statistically consistent with these observational changes. And if we are to collect some statistics, the R-square actually increases from only 0.24 to 0.42, which is significant with p smaller than 0.05. And this result also indicates that current models are able to reproduce historical North Atlantic hurricane frequency once given sea surface temperature or the biases in sea surface temperature is better removed. So finding that sea temperature biases in sea temperature is the major limiting factor for models to reproduce the long-term historical hurricane activity is actually good news for both the hurricane community and for the SST reconstruction. So to some extent, it provides an independent evaluation of the scale of our sea surface temperature correction, right? But it also demonstrating that correcting or accounting for these regional SST biases on the order of only several tenths of a degree Celsius is still important. So this improved hurricane simulation is my third example. And let's just give a brief summary of my talk. So in this work, we combine statistical, physical, and historical evidence to improve the quality of historical sea surface temperature, a fundamental data set for studying climate change and weather patterns. And now we have a much better opportunity for the whole community to better understand past climate change and weather extremes. These include, but not limited to, a uniform early 20th century warming, the removed World War II warm anomaly, and increased hurricane simulations. Of course, there are still some other jobs to be done in terms of further improving the quality of historical sea surface temperatures. For example, as I mentioned, developing that absolute bias correction, and at the same time, how to infill sea surface temperatures to cover areas where we do not have measurement is another important question that we need to tackle or work on in the future. But in short, the better we understand the past, the more precise that we can predict the future. And I'm just going to stop here and begin to take questions. Thank you so much for your attention.
Great, thank you so much, Duo. If anyone has a question, feel free to raise your hand or write it in the chat and I can read it out. I think Jared has a question. Do you want to go ahead?
Yes. Hello.
Hi.
I really enjoyed your talk. I was curious, at one point you mentioned that your future work is going to be leaning more towards, instead of looking at relative biases, looking at absolute biases.
Right.
And I am curious how the method that you described of, I guess you sort of briefly touched on it, of linking these to existing temperature measurements so that we can figure out what the actual absolute temperature is. How is that process distinct from what you described some of the other existing sea surface temperature data sets doing to correct their biases of we're just gonna clamp it down by something else that we already know and assume that fixes it? What is it about what you're doing that is unique from that?
Okay, I see. Yeah. So first is that, our absolute correction is still derived for the basis of individual groups. So each group will have a unique absolute correction. This differs from existing works that still clumped everything together. And at the same time, as I mentioned, right, we want to use the land air temperatures from coastal and island stations. So in order to use these temperatures, you actually need to account for the fact that these air temperatures on the land warms relatively faster than the sea temperature, and they have different magnitude of, for example, interannual variability from year to year. So basically, we would need to first scale and pre-process these air temperatures such that they look like sea temperatures, and then we can use them to adjust these historical sea temperatures. And in previous studies, that adjustment was done in a very crude way by using only one scaling factor that is not a function of region or seasonality. But we all know, right, this differential warming or temperature variability is a function of region, season, and also even frequency bands. So one of the work that I'm working on is to really define a much more resolved scaling algorithm that allows for accounting for these regional, seasonal, and frequency dependent differential variabilities, such that we can making use of these station temperatures in a more sensible way.
Thank you. That addresses my question. Thank you.
Okay, thanks.
Any more questions? Yeah, Andrea?
Hi there, Duo. Thanks for a really great talk. I was just wondering, so you didn't really talk about any biases that could be from the thermometers themselves. And I was wondering how much you think that might be contributing to past biases and temperatures.
Right. So I would say like these, if there are any systematic biases in thermometers, that will be captured or picked out by the statistical method, right? But again, like when we use physical or these historical like evidence to understand these offsets, I think like, you know, systematic changes in like the bucket characteristics or this engine room heating that really stand out. So I would say these problems associated with measurement method are of the first order. And I agree, like it's possible we still have these biases in temperatures, but I think with really limited metadata, we probably cannot attribute that specifically from these statistically constrained signals. Thank you.
Great. Thanks, Andrea. So any final questions? I'll ask one maybe wrap-up question. So you showed all sorts of issues lurking in our SST data. Do you think that if you dug into, say, precipitation data or some other kind of station or in-situ-based observation data set, could a thesis be written about any of these data sets, or is there something specific about the SST data that's made it more prone to these issues?
Right, it's also a very good question. So I think these oceanic, not only limited to SST, but these oceanic data set differs significantly from these land station data set in the sense that for land station, right, the same station is always sitting there, and it's the same amount of people get similar training using more or less systematic measurement instruments or methods, right? So this Eulerian perspective like measurement practices would more or less give more homogeneous or homogeneous like quality of measurements. Whereas over the sea surface, probably these merchant ships would not try to, you know, stay in a fixed point, right? So actually at a specific location, it's always sampled by different agents. And that gives you a big possibility for various like offsets arising from changing agents and which could interact with their relative offsets. So I would say my technique should definitely be applied to measurements coming from these like other physical quantities in this historical like archive. But you know, like although I said like the land problem is less, there are still like they could still suffer from problems. For example, if there is a moving in the station, or as the urbanization develop, as the cities developed, right, the urbanization would have some impact on these stations. So people have been applying, I would say, similar techniques, but simpler techniques, basically comparing one station with its surrounding neighbors and try to estimate or pick out sudden changes or let's say unusual or abnormal like signals in these station temperatures.
That's fascinating and yeah, interesting to consider further. All right, well, we're over time, so I guess we should head out, but thank you so much again, Duo. This has been great having you here, and please, anyone, if they have more questions for Duo, feel free to follow up with him via email or otherwise. So,
okay, thank you.